Thanks for the introduction. So I'm Stark. I'm an applied data scientist, and I'll be talking the first half and then hand it over to my colleague Hanieh for the second half. So in this talk, I will go through a case study where our data science team design and implement a series of sensitivity analysis, which has helped us improve our understanding of our machine learning models and also helped us improve our models in real applications. Just as a brief introduction, at Lydia.ai, as an insurtech startup company, our mission is to insure the next billion people. And we do that, and we believe that the next generation of insurance products should be based on the use of dynamic data in order to offer continuous and dynamic risk prediction. And we do that by leveraging alternative data for personalized insurance risk prediction. And by alternative data, we mean any data that is not traditionally used in the insurance industry, which I'll come back to this later. And in our data science team, we accomplish this goal by going through or by iterating our machine learning models through the machine learning lifecycle. So we start with our data and we train our models, and we validate our models, and then finally deploy them. And for today's talk on sensitivity analysis, we'll be focusing on the stage of model validation. But let's come back to the data first. What differentiates us from traditional insurance companies is the usage of alternative data. And one example that we've been working on for a long time is electronic health record, which basically represents a personalized medical history. And we believe that contains information that's predictive to the long-term trend or the long-term risk in the person's health or mortality. And we have actually iterated our electronic health record model through this machine learning lifecycle, and it works quite well. More recently, we've become interested in another type of alternative data, which is human mobility, because we believe it has the potential to offer continuous and dynamic monitoring of health risks in the short term. Wearable devices such as Apple Watch, Fitbit, they collect a vast amount of data on human mobility in the form of, let's say, accelerometer data or step count per minute as a time series. As a proxy of the general level of activity, you might imagine that mobility data can be a proxy of the general level of health for an individual. After all, the more active you are, the healthier you tend to be. And this is why we've become interested in this type of alternative data. And we've actually started with a step count time series, which is collected over 7 days. And we've experimented with it and then successfully built a deep learning model on this to predict the mortality risk of an individual. As you can expect, working with this type of data, alternative data, whether it's EHR or mobility data, can be challenging, not only in terms of building the model, but also in terms of validating the model. And this is especially true in our application, which is the insurance industry, which tends to be more conservative when it comes to taking new risks, in addition to the highly regulated environment. And that's why we've come up with a fairly comprehensive validation framework for our models. And this framework has already been introduced in last year's event, TML's event, and we'll be happy to talk more about it after this talk. Basically, on a very high level, in this validation framework, we would like to get the acceptance of our ML models from all stakeholders involved, for example, our data scientists, as well as domain experts in the insurance industry, such as the actuaries and the underwriters. And we do this by presenting our models from their perspectives. For example, for the data scientists, we look at the standard machine learning metrics and also some standard metrics for machine learning model explainability. And in order to get the acceptance from our actuaries, we actually show them some numbers and plots in terms of incidence rates, which tells them whenever our model says someone is risky, they are actually risky in terms of mortality. And finally, in terms of underwriters, we have also produced some charts and numbers that shows that our models are making predictions that are clinically reasonable in terms of some medical information. The key message here is that we already have a fairly comprehensive framework for model validation. And it worked quite well for our long-standing model on electronic health record. But then when we started to move on to mobility data, we wanted to do better. Because the mobility data, the time series on a step count, is actually quite different from what we used to work with. And the model that we come up with is also considerably more complex than before. So we really wanted to do something extra in order to further validate our model and also boost our confidence in the model's prediction. And that's motivated us to come up with a series of sensitivity analysis in order to further see the model's behavior. And by sensitivity analysis, I mean the sensitivity of model prediction with respect to the changes in the model input data. And this is illustrated by this diagram. So suppose that I have some data as my original input, and I run it through my model, and then I get some original output. And then on an alternative scenario, I will perturb or modify my original input, and then run it through the same model, and then I'll get a perturbed output. As you can imagine, whenever I change the input of my model, the output may or may not change. And if it does, the change might be small or big. And the change is precisely the focus of our sensitivity analysis. So in our sensitivity analysis, our goal is to investigate the change in our model prediction when we intentionally modify or change the model input. And we'll see some examples of how we actually come up with these scenarios later on. But first, I would like to point out some key characteristics in this framework. First, our analysis is post hoc, so everything is done after training the model. Our analysis is also model agnostic, meaning that we haven't really made any assumption on the underlying model. The only thing that we care about is the change in the input and the change in the output. And consequently, another advantage is that this framework for sensitivity analysis is very easy to communicate with non-technical stakeholders, such as our actuaries and underwriters, because we are only, again, concerned with the changes in the input and output, but nothing about the model itself. As data scientists, one type of question that we typically get from non-technical stakeholders is the what-if questions. They might ask, how would your model behave in a hypothetical scenario? And this framework for sensitivity analysis can partially address that type of questions. And finally, in terms of implementation, we only need to be creative and also be careful when we actually design the sensitivity test scenarios, basically how we actually perturb the original data. And this modification can be actually motivated by the real data that our model is expected to see in application. On the other hand, it might also just be some artificial changes that might be completely implausible in practice, but we might still be interested in checking the behavior of our model in those edge cases. And here are some examples. So on the first row, you can see a sample of our original data, which is a time series of step count collected every minute over 7 days. So you have our original data over there. Suppose that we're interested to see how the data or how the step count in the first day would affect the model prediction. And what we can do is to use the sensitivity scenario in the second row. Basically, I can create a scenario where I remove all the step count in the first day, and then I make another prediction. And then the change in the model prediction will sort of represent the overall effect of the step count in the first day. And you might wonder, by removing the first day completely, we're actually removing a lot of information, in particular, the mean and the variation, or particular, the patterns of the movement. That's what motivated us to come up with 2 more scenarios. In the third row, we are removing all the variations in the first day, but we keep the same mean as the original. And then this is to investigate the effect of all the variations in the first day. And similarly, we can keep the same shape, but only parallelly move up or down the step count in order to investigate the effect of the average in the first day. And you might expect, as you can imagine, we can extend these scenarios to any days in the 7 days, or in fact, any combinations of multiple days. So that's some artificial perturbation of our input data. Here are more examples that's motivated by the real application of our machine learning models. At the beginning, I said we would like to offer a continuous and dynamic risk monitoring for each individual. And that means in practice, we can expect our users of our model to get a prediction regularly, let's say on a daily basis. In that case, it would be interesting and important to investigate how our model prediction would change for the same person over time. On the first row, you can see we still have the original data over 7 days. Let's say someone wants to calculate their score on the 8th day. What I can do is augment a new data where I shift my original day 2 to day 1, and then day 3 to day 2, so on and so forth. And then I will make the assumption that the movement in the 8th day is the same as the first day. And then that will create a synthetic sample that's mimicking the scenario where someone gets their score on the 8th day. And then I can do this by rolling my step forward day by day. And then I can create samples that continuously monitors the prediction of our model over time. So those are just some of the examples of our sensitivity scenarios. Just to go back and then recap what I've talked about. So we came up with this framework for model sensitivity analysis. Basically, the overall idea is that we perturb the input, and then we're interested in the changes in the output. And they want to see whether the change are interpretable, reasonable, and make sense intuitively to a human. Now I'll hand it over to my colleague Hanieh to talk about how this framework has actually helped us in real applications.
Okay, so for the rest of this presentation, through an example, I'm going to show you how sensitivity analysis helped us understand some of the model behavior that by itself, it's not a problem, and it's one of the characteristics of the model based on the data that was trained on. But then for our case and for our application, it becomes a problem. It needed to be addressed. So Spark earlier introduced to you the sensitivity scenarios that we've designed for this project, but I want to focus on 2 of them in particular. Okay, sorry for the echo. So the first one is when, like this? Okay, so the first one is when we remove different days of the week and replace it with 0 activity. So here you can see the time series data when we remove different days of week one by one. So we did this for example, we zeroed day 1 for all the samples within our test set, and we calculated the mortality prediction, and we then compared it to the baseline prediction. And then we repeated this for each days of the week, one by one. And here you can see the histogram of raw model prediction change compared to the baseline model when we zeroed each day of the week. And I want to focus on 2 days in particular, day 1 and day 7 here. So when we zeroed the activity of day 1 and calculated the mortality prediction and looked at the change, we saw that in average, the prediction went up, meaning that the person becomes unhealthier, which is understandable. If someone is less active, we expect them to be unhealthier. But when we looked at day 7, and when we removed day 7, we saw that on average, the model prediction goes, the probability goes down, meaning that the risk goes down. So the model thinks that the person is healthier if we remove day 7, which is not intuitive. So this showed us that the model behavior with respect to different days is different. And also the model behavior does not always align with our expectation. So the second scenario that I want to talk about is rolling different days of the week. So this is assuming that the activity level of the person stays the same. And by doing this, we'll get a different snapshot of their activity. So here you can see the time series data when we roll different number of the days within a week. And we did the same thing. We looked at the raw model prediction. And here you can see an example of 2 different cases with like rolling different number of the days. And what I want you to focus here is how the raw prediction, the change is, the range is wide. So keep in mind that the probability is from 0 to 1. And the change here is from -0.4 to +0.4, which is significant. So this again told us that the model is dependent to the order of the days. So to understand why the model is behaving like this, this goes back to our training data. So the training data got collected during a fixed 7 days. And this is usually the case for any data that gets collected using variables. They get collected during a certain fixed duration. So in our case, participants were given the device on day 1, and they had the device for 7 days. So when participants initially got the device, some of them might be more motivated to go for a walk and be more active. And on the other hand, during the later days of the week, more people, because of the participant compliance, might stop wearing the device or being active. So the model understandably learns that the order of the days matter. So I'm going to talk about why this was a problem for us. And I'm going to do this through an example. So these sensitivity experiments were around the same time that some of our colleagues wanted to train for a marathon. So they were training for a marathon, and at the same time, they were syncing their smartwatches with our mobile application shown here at the left side. And we were able to analyze their data and their score while they were training for the marathon. And by the way, here is a picture of them after finishing the marathon. OK, so here I want to show you the 2 weeks of the training for marathon for one of our colleagues. So if you look at these 2 weeks, we can see that the level of activity is pretty similar. In average, this person was walking 14K every day for during a week, and they were pretty active. However, if you look at the pattern, we can see that for the week shown at the right side, the person was more active during the first half of the week. And then for the week shown at the left side, the person was more active during the latter half of the week. And when we look at the model prediction, we saw that we get a much higher prediction for the week that's shown on the left side, meaning that when the person was more active during the latter part of the week, the model thinks that they're unhealthier. So having done the sensitivity analysis and seeing these results, we exactly know where the problem is. And OK, so I talked about how the model was dependent on the order of the days based on our training data. But for our case, this is not a correct assumption. This is because this colleague, for example, they could submit their data to get the model score today, and then they could submit it again tomorrow, and then the day after tomorrow. So the order of the days change. And by changing the order, we should not get a different model score. So this means that if the model score changes, it means that we can get different scores for the same level of activity, which is not good. Right? And then it also affects the trust of the user, of this colleague, in the model score and the prediction. So this needed to be addressed. And there are multiple ways of doing this, but one way that we decided to go forward was shuffling the days during the model training and retrain the model. And I'm going to present the result of that for the next slides. OK, so once we trained the model, we went through the model validation framework that we already have. And we also repeated the sensitivity analysis to make sure that the issue is gone. So here you can see the same results for when we remove day 1 and day 7, when we replace it with 0 activity. And we can see that in both cases, the model prediction in average goes up, and the behavior is consistent for different days, and it's also what we're expecting. If the person is less active, we expect them to be unhealthier. For the rolling different number of the days of the week experiment, again showing 2 different examples here, but we saw that the raw model prediction, the change range this time is much smaller. So this is 1/10 of what we saw before, right? So by repeating these experiments, we confirmed that the dependency to the order of the days is gone. We also looked at the real examples that we had from our colleagues. And this time, we're getting a much more realistic and closer prediction for those 2 weeks of training. So today with this case study, we just showed you one example of how sensitivity analysis helped us understand the model behavior and issues within our model way before deploying the model. But this is just one example. We're actually using sensitivity analysis for different types of data, for different types of model. And we've already incorporated the sensitivity analysis within our model validation framework. And for different projects and for different types of data, we just need to design the sensitivity scenarios and come up with scenarios that help us understand the model behavior. But yeah, so I want to invite all of you, if you're not using it already in your work, think about how you can incorporate this in your work and in your project and to understand the model decisions better. And in summary, we talked about the rigorous model validation that's needed in regulated industries like insurance. And we've looked at sensitivity analysis as one option of understanding the model behavior. And we've shared some of the sensitivity scenarios that we've designed to understand the model behavior and how we utilize those analysis to understand the issues within our model, and then use the same analysis to, once we come up with a solution, to make sure that the issue is gone by incorporating the sensitivity analysis within our validation framework. And that finally, the analysis that we showed here can be extended for different fields, different applications, and just needed to think about the sensitivity scenarios that make sense for your work. Thank you so much. We're happy to answer any questions.